Hey, welcome back. All right, so now we're going to take a look at the next thing here in Module 10, and it's hypothesis tests about two population means, where the population standard deviation is known. And so these are pretty specific scenarios, specific situations, and what you're just learning about is different situations where you could apply statistics to get some insight. And so it's kind of like you're learning different tools for different situations. And I don't know, the example that comes to mind isn't the best one, but like if you were in the military, you would be like, well, if you need to shoot something at a far distance, you'll use this rifle, a sniper rifle. And if you need to do close quarters combat, you'll use this tool, this shotgun. And so you have different tools for different situations. Another example might be like if you're in a woodworking shop, and if you needed to, do what do they call that? Butterfly joints, I think they are, something like that. You would use one tool, but if you needed to do polishing, you might use a sander. So you have different tools for different situations. So you're just learning different tools for different situations. And so if you look at like what is a hypothesis test about, like if you're ever in a situation like this one in the example, this is the best way to explain it, where you have two different testing centers and you want to see if the results between the testing centers are different or if they're the same. If you want to see like, are they doing equally well, or is one doing better than the other, you could do that. And so here's this example of a training center, and a standardized exam was given to individuals who are trained at two different centers to evaluate the difference in education quality between them. And so you're going to have the mean of the population, right? At one center, how do they do on the standardized exam? What's their mean? What's their average score on that exam? And then at the other training center, what's their mean? What's their average score for the population on the exam? And we're going to make inferences about the population mean, the average score on the exam from each of these populations, each of the centers. We're going to make inferences about what that actually is based upon the sample that we do. So here's the mean examination score for the population of individuals trained at Center A. Here's the mean examination score for the population of individuals trained at Center B. And can we conclude using level of significance? Is that what that's called? Level of significance? No, it's level of significance, alpha. Can we conclude at a level of significance of 0.05, level of significance of 0.05, which means our confidence level is 95%, that no difference exists between the training quality provided at the two centers. So the first thing we have to do is we have to develop a hypothesis about these training centers and the differences between their means. And what we said about hypotheses tests is when you develop a hypothesis, that in the null hypothesis is where you always put equality. And so here are the different types of hypotheses you could develop for these kinds of situations where you have a difference between the means. And so for a two-tailed test where it could be like, hey, you're too much or you're too little, so we're going to be kind of testing it against both tails, the null hypothesis is where equality resides. And you can see here that equality, greater than or equal to, less than or equal to, is always in the null hypothesis. And so that's just a little rule of thumb. You could remember that when you're putting together your hypothesis, it's the current state, it's the status quo, nothing's changed, there's no change, it's the status quo, current state, right? And it's also where equality is, right? So here our null hypothesis is going to be the difference between these two are equal to 0, and that's the difference sub 0. And here the difference between these two is not equal to 0, and that's difference sub 0. And then to calculate this, we're going to use Z. I love it. Z. I understand Z. Z table, comfortable to work in it. And so here we're going to have this formula here. And if you just take a look at that notation in that formula, you can see sample. Well, let's bring up our little notation guide. So our little notation guide is right there. But we have sample mean minus the differences for what we're hypothesizing here, which is the difference is going to be 0. So I guess there could be situations where you have a difference that's not 0, but in this example the difference is 0. And then these are the population standard deviations. You can see that notation right up here. And then this is the sample size, the lower n. So here is the question, and then here is all the data from the samples. Sample size, sample mean, standard deviation, and again, this is standard deviation of the population. And then if we do that, again, here's that data over here to the left. If we take this test statistic formula and we do this calculation, put all those numbers into it, we get 1.66. Okay, and so when we graph this out, I like drawing this little thing, and I put here that D0 is 0 is kind of like that's the hypothesis, is that the difference between these is 0. So I put that there, and then we're looking to see like where did our sample stuff come in. And we want to do this with a 95% confidence level, so it's a two-tailed test. So this is going to be our level of confidence, and then over here will be where our alpha is. And if our level of confidence is 95%, then our alpha is 5%, and half of it will be here, alpha divided by 2, and half of it will be here in this tail, alpha divided by 2. And so from this point over is 97.5% of our data, and if we look up 97.5% of our data, we get 1.96, which is right there, 1.96. And so we graph there, 1.96, that's our z-value. And then our p-value associated that is 0.975, right? It's 0.975, and so 0.975, and that's because it's 97.5% of our data from that point to the left. And then we calculated a z of 1.66, and if we look up that z of 1.66, how much probability is from this point over to the left? And if we go to 1.66, we get 0.9515, so that's our p-value. And so from this point over to the left is 95.15% of our data. Well, we're well within this area here where we do not reject the null hypothesis. So we accept the null hypothesis, and by implication we reject this one. And so we could say that the difference between the two population means is 0. And I really like doing it this way, just thinking about what's my z-value and thinking about what's my probability of this much data from here to the left, and they call that the p-value. But then they also give it these names. This is the critical value approach. So this would be the critical value, 1.96, and this would be the test statistic. And they actually call it that, the test statistic. So you can see here that's called the test statistic. And then they call this the p-value approach. But for me, just thinking what's my z-value, what's my p-value, graphing this out, and putting down where's my p-value and z-value, this just makes it way more clear for me. So just taking a look at how the book kind of put that all together. There's this slide here where they develop their hypotheses, and then there's this slide here where they do the calculations. And because this is kind of a, takes a little bit of work to do that calculation, I just put in what the book had as my calculation. So, instead of working it out manually, which, all this math here we should do, but we should all know how to do this, but it's pretty, it just takes time. It's a couple of minutes, so I just thought I'd save it from the video. All right, so they do their math there, and then for the p-value approach, they have a slightly different way of doing it, which really doesn't make sense to my brain. But the main points here is for a z of 1.66, the area to the left is 95.15, 1.66, 95.15, and that's their p-value approach. And they also come to the conclusion that there's no difference, right, between the quality and the training center, so we cannot reject H0. And then for their critical value approach, or their z-value, 1.66 is less than 1.96, 1.66 is less than 1.96. And so they also say that we cannot reject because of that, and there's no difference in the quality of the training centers. So that's kind of a cool situation. Again, just another tool for your toolbox. You get into different situations. You might need to use this tool for one situation, that tool for another situation. And so here, if you wanted to know, hey, is there a difference in the quality of two teachers when they both administer the same exam, or is there a difference in the quality of education when students at one institution are taking this class and they're taking the same class at another institution? Do you get better results at one place or another? You could use this, right? You could use this tool. So you just say, oh yeah, what's that tool? You go look it up, you bring it out, you use it, and then you have a confidence level that there is or there is not a difference, and that's kind of cool. All right. See you in the next video. Keep up the great work. You're doing great. If you're watching these videos, I totally commend you, right? That's amazing. And just keep doing it, keep showing up, and you're going to progress. You just keep showing up and you're going to progress. Just keep doing that. You're going to do great. You'll get a good job. You'll have a good house. You'll be able to have a nice car. Life will be good. Just keep going to school. See you in the next video.